Dimensions are one of the most important tools in physics. A lot of smart guys out there have been using this tool to correctly answer some physics questions, even without having a clear understanding of the questions. While we encourage understanding physics as the surest way to answer questions correctly, isn't it great that there is a way to do some tricks? Now, what is the whole idea behind dimensions? But before we go into that, can you remember the fundamental quantities? Oh, yes, here they are. What about the derived quantities? Of course, there are too many to be listed. But we recall that the derived quantities depend on the fundamental quantities. Now, nearly all of the countless number of quantities we have in science are derived quantities. Now, the whole idea behind dimensions is to build an elegant way of relating all these quantities together. Think about this. If we can first relate each of the derived quantities to the fundamental quantities from which they are derived, then we have indirectly built an excellent way of relating the derived quantities also to each other. That is exactly the idea behind dimensions. First, relate each of the derived quantities to the fundamental quantities, and by doing this, you've also related the derived quantities to each other. Now let's set this ball rolling. We will start by stating the dimensions of the fundamental quantities. Oh, again, here they are. Observe that all the dimensions are usually indicated in capital letters, or as we call them, uppercase. Mass, you can see, is represented by M. Length is L. Time is T. Electric current is I. Temperature is the uppercase of the Greek letter theta. Amount of substance is N. And luminous intensity is J. So these are the only 7 letters we may use to represent the dimensions of all other quantities. They are M, L, T, I, theta, N, and J. Now let's illustrate with the dimensions of some derived quantities. We will start with area. Area is given by length multiplied by width. Both length and width are lengths. So the dimension of area is going to be L multiplied by L, and that gives us L squared. Next, let's try volume. Volume is given by length multiplied by the width multiplied by the height. Length, width, and height are all types of length. So the dimension of volume is going to be L multiplied by L multiplied by another L, and this gives us L cubed. Then speed. Speed is given by distance over time. Distance is length, so the dimension is L. And the dimension of time, you remember, is T. So the dimension of speed is going to be L over T, which is the same as L T raised to the power of minus 1. Then let's take on velocity. Velocity is displacement over time. Displacement is also length, so the dimension will be L. And the dimension of time is T. So the dimension of velocity again will be L over T, which is the same as L T raised to the power of minus 1. So we see that both speed and velocity have the same dimensions. In fact, they are very similar quantities. The only difference is that to specify velocity of an object, the direction in which it is moving also has to be additionally specified. In a similar way, distance and displacement are similar quantities, except that to specify the displacement of an object, the direction also has to be additionally specified. Quantities like speed and distance, which do not require direction to be additionally specified, are called scalar quantities, while quantities like velocity and displacement, which require direction to be additionally specified, are called vector quantities. We will have a detailed treatment of scalar and vector quantities in another lesson. For now, we will continue a further treatment of dimensions in our next lesson. See you guys there.